Welcome to section 313. We're going to be talking about an application of exponential growth. We're going to be talking about interest. So we're going to kind of skip around a little bit. We're going to go to problem 2A. Actually, it doesn't have a number. But we're going to be talking about compound interest. Now, compound interest, that's 8%. So that's our exponential growth. So it's going to be in the form of y equals A times 1 plus r to the x, where x is the number of years, and r is the rate as a decimal, and a is our initial. So our rate is 8%, which is 0.08. So we're going to be looking at this and finding out what would our balance be at the end of the fourth year. Like I said, we're skipping around a little bit. So for our equation, we can write y equals, we're starting with 1,000, that's our initial, 1 plus 0.08 to the x. So y equals 1,000 times 1.08 to the x. That's the model we can use to determine how much money we'll have in our account at any year. So for part B, x equals 4. So y equals 1,000 times 1.08 to the fourth. So when you do that, you get y equals $1,360.49. Because we're talking money, we're going to go 2 decimal places. So that's how much we'll have at year 4. Going to the next page, part D for this, we're going to find out how much we'll have at 20 years. So y equals 1,000 times 1.08, and now it's year 20. So we type this in our calculators, we get $4,660.96 is how much we'll have in 20 years. That's regular compound interest. Now we're going to be talking about compounding multiple times per year. So we talk about multiple times per year. So ignore this simple interest. We're just going to go compound here, and that's once per year. And compound interest compounded n times per year. So now for compound interest, y equals a times 1 plus r to the t. So a is our initial. R is that rate as a decimal. And t is the number of years. You can use x as well, but you'll commonly see it as t. Now, compounded n times per year, it's very similar, except we're adding a little bit more. Y equals a times 1 plus r over n to the nt. Now, a and all of that is the same. The only thing that happens is n is the number of times per year. So if we think about like weekly, that's when n equals 52, because there's 52 weeks per year. If we think about monthly, for example, n is going to be 12 because there's 12 months per year. If we're thinking daily, n would be 365 because there's 365 days in a year. So that's a way we could think about it. The only difference is we have n. Now, when we're just compounding once per year, n is just 1. That's why they're the same equation. You could use this for all of them, except n is 1. So you'd just be dividing by 1, which doesn't change anything for the r, and you'd be multiplying the t by 1, which doesn't change anything. So here we're going to do a problem, number 2. When we were born, 500 deposited into account, 1.25% annual interest represents compounded monthly after t years. So when you see those words, compounded monthly, that means you're using it for multiple times per year. So y equals a times 1 plus r over n raised to the n t. So for this, a, the initial is 500. The rate is 1.25%, which is 0.0125. N is the number of times per year. If we're talking monthly, there's 12 months per year, so n is 12. And for this, it says after your 18th birthday. So we'll come back to that. So for the first one, y equals 500 times 1 plus 0.0125 divided by 12 to the 12t. That's the model we could use for any number of years. So for this, the 18th birthday, 500 times 1 plus 0.0125 divided by 12, all raised to the 12 times 18. Make sure you put parentheses around those exponents. So when you type that into your calculator, you're going to get about $626.09 in your account after 18 years. And that's for the monthly. Now, for the second part, it says, how much would it be if you compounded daily? Now, let's see how much of a difference. So that would be n equals 365. So y equals 500, 1 plus 0.0125 divided by now 365, all being raised to 365 times t. That would be the basic one. So y equals 500 times 1 plus 0.0125 divided by 365 raised to 365 times 18. So you can see when you type that in, you get $626.16. Changing it to daily made very little difference. We got about, 7 more cents for daily? So it doesn't make that much of a difference because you're dividing and then just multiplying. So makes not much of a difference. So there's that other type, that compounded monthly, daily. Here we have 5,500 new account, 3% annual interest, 5 years if it's compounded semi-annually. When you see semi-annually, n equals 2. 3.6 is 0.036. So y equals a times 1 plus r divided by n to the nt. So y equals 5,500 times 1 plus 0.036 divided by 2 to the 2t. That's the model for any number of years. So if we're looking at 5 years, 5,500 times 1 plus 0.036 divided by 2 to the 2 times 5. And our value would be $6,574.16. That's our balance after 5 years. Next page, we'll do a couple more of these. Same thing, except now we're looking at monthly. So n equals 12. So y equals 5,500 times 1 plus 0.036 divided by 12 to the 12t. That's the model. So 5,500, 1 plus 0.036 divided by 12 raised to the 12 times 5 because it's 5 years. And you're going to have about $6,582.92. And then finally, daily, that's when n is 365. So y equals 5,500 times 1 plus 0.036 divided by 365 raised to the 365t. 5,500, 1 plus 0.036 divided by 365. 365 times 5. So y equals, and you're going to get about $6,584.64 for that one. That's after 5 years. So there's that when you see it compounded daily, monthly, weekly, and so forth. Next, we have a pheasant farmer starting with 120 pheasants, and the population is increasing 15% each year. So there's not that per month or anything like that. It's just each year. So it's going to be that regular exponential growth. Y equals A times 1 plus R to the T. So y equals 120. That's the initial. 1 plus. Now the rate, 15% or 0.15 to the T. 120 times 1.15 to the T. That's the model for any number of years. So if we will look for 10 years, y equals 120 times 1.15 to the 10th. So you get 485.47. Now, we're talking about living creatures. We don't want 0.47 of them, so we're just going to round down. So we're going to have about 485 pheasants. Now, if we're looking at population growth. So now, the rate, and it's an annual rate, so it's per year, of 2.4%. So we're going to use that regular exponential. Y equals A times 1 plus R to the T. So we have our initial population, which is 330,000, times 1 plus. Now, 2.4 is 0.024, and then T is the number of years. So Y equals 330,000 times 1.024 to the T. There's our model. Now we're looking at the population in 2040. Now, we're starting year 0 is 1970, so our T, our exponent, is going to be 2040 minus 1970, so T is 70. We're looking 70 years into the future. 330,000 times 1.024 to the 70th. So you're going to get 1735844.848. So y equals, we're going to cut that off, we're going to round. So we're going to get 1,735,844 people. That's how much the population increased. And you can see there's that exponential growth. We didn't see those words daily or weekly or monthly. That's why I used the basic compound growth. Okay, and that is it for this section. Make sure you pay attention to which equation you should use and when. And have a nice day.